In section 2.1, we'll be going over the limit definition of derivative. But first, let's review what a tangent line is. So back in geometry, you might have talked about a tangent line being a line that touches a circle in just one point. But we want something more specific when we talk about curves, because as you see here in these examples, sometimes a tangent line can cross a curve at a second point, or maybe even more than that. So we want something a little bit more specific. And so our definition of a tangent line is thinking about a function or a line, that passes through a point C, f of c, and so that's a point that it shares with the graph, and slope m, where m is this equation here. So remember, this is what we figured out in our activities. So the slope of a tangent line is the limit as x approaches c of f of x minus f of c over x minus c. So essentially it's the slope of the secant line, but we're letting x and c get closer and closer together. So if that's our slope and we go through the point, then that will give us what is called the tangent line. So something that's important to realize here is that the slope of the tangent line is equal to the slope of the graph at the point of tangency. So at that point that they share. So in example 1, it asks us to find the slope of the graph of f of x equals 2x minus 3 at the value x equals 1. That's the same thing as finding slope of the tangent line. So we're going to use our formula, m, so that's our slope, subtan, just slope of tangent line. So I'm going to say that the limit as x approaches 1, so our c was 1 in this case. And then I have f of x, which is 2x minus 3, minus, now I need to find f of 1, and so I really just need to plug 1 into my function f. So 2 times 1 minus 3 is negative 1, all over x minus 1, x minus c. Let's go ahead and simplify that before we try to find the limit. I just put the parentheses in the first step to just separate my f of x and my f of c. So f of x minus c up here, this is going to become a plus 1, so I have 2x minus 2. That simplifies to 2 times x minus 1 over x minus 1. So I can cancel that out. And so I have the limit as x approaches 1 of 2, which is just 2. There were no variables left for me to plug in there. And so that should make sense with what we know about the graph of 2x minus 3. It's just a line with slope 2. And so anywhere I draw a tangent line would also have to have a slope of 2 because it's already linear. Where these types of problems get more interesting is when we have something that's not linear. So that means the slope is not constant, it's changing. So we're going to set up the same kind of formula here. Our function is x squared plus 1. We are also at the value x equals 1. Let's go ahead and find f of 1. It is 2. So 1 squared plus 1 is 2. So my limit as x approaches 1, my c value is f of x, x squared plus 1, minus f of 1, which was 2, all over x, minus my c value 1. Let's go ahead and simplify that as well. So I have x squared minus 1 over x minus 1. If I try to evaluate this right now by plugging in the 1, I will get 0 over 0, which we know means there's something else we have to do. So we have to go back to our limit techniques from Unit 1. I will factor the numerator. And now I see that my x minus 1's cancel. So I have the limit as x approaches 1 of just x plus 1, which is 2. Now, that doesn't mean that my slope is always 2, it's just at that point. So if we think about the graph x squared plus 1, it would be a parabola shifted up 1. And so at the point x equals 1, if I were to draw a tangent line, the slope of that line would be 2. Also, the slope of the graph then would be 2 at that point. So that equation for slope of a tangent line is really, really important in calculus. And so we actually have a special name and notation for it. So the notation we use is f prime of c. So it's like f apostrophe of c, but we read it f prime of c. So that is the slope of a tangent line to a function f at x equals c. So it's slope at a particular point. It's that formula we've been talking about, f prime of c, and this is called the derivative of f of x. So about half of what we cover in AP Calculus is going to be derivative. This is a super, super important concept. So f prime of x is the derivative of f of x. So when you hear derivative, you should automatically think slope of the tangent line, okay? And when you hear slope of the tangent line, you should automatically think derivative. Those are synonymous to us. Now, what we want to start thinking about, though, is instead of just having to find the slope at one point, could we start to think about the slope at more points? And so before we get to that step, let's break it down a little bit more. So instead of having these two separate points, x and c, we can think about x just being a point c plus h. So h here is just the distance between the points. So we have c and c plus h. Those are my points. And so the distance between them is h. And so if I plug that in for x, I would have c plus h in for my x. I still have c here. In the denominator, I would have had c plus h minus c, which would just simplify to h as it does there. And the other thing is, sorry, this got erased. If these 2 points c and c plus h are getting closer and closer together, then that means h is actually getting closer to 0. So the distance between them is approaching 0. So you'll notice here that this formula has the limit as h approaches 0. So it's the same, it's not the same exact formula, but it will find the same thing as our formula up above. It's just a different format, and you'll have to be able to recognize and use both formats. So let's actually use it to find the same slope as we did in example 2. Okay, so again we have the function f of x, which is x squared plus 1, and we're at the value x equals 1. But this time we're going to use the alternative form of the derivative, which was given right here. And so if it didn't tell me what form to use, I could use either one. It's up to you, but this one it tells me. And so we're going to start using that derivative notation. So if I'm asking for the slope of a tangent line at 1, then that's f prime of 1. So this is equal to the limit as h approaches 0 of f of, now this x equals 1 is my c, so 1 plus h minus f of 1 all over h. I don't stop there. I actually want to evaluate what f of 1 plus h is. And so think about f. It's x squared plus 1. I can think of that as something squared plus 1. It all depends on what is inside the parentheses there. That tells me what I'm plugging in. So for f of 1 plus h, that means I have something squared plus 1, but that something squared is 1 plus h. Minus f of 1, so there I'm plugging in 1 squared plus 1. Okay, so I'm just evaluating, I'm replacing the x with a 1 in the second term. In the first one, I was replacing the x with a 1 plus h. This is all over h. Now, if I tried to plug in h equals 0 right here, I would also get 0 over 0. So we're going to try to algebraically manipulate this. So remember that when you expand 1 plus h squared, you actually have to think about it as 1 plus h times 1 plus h, which means you have to FOIL. So this is 1 plus 2h plus h squared plus this 1. And then we have 2. 1 squared plus 1 is 2, so this is minus 2. all over h. I can see here if I add the 1, and the -2, those will cancel out. So what I'm left with is 2h plus h squared over h. I'm going to go ahead and rewrite that. Now what you should notice at this step is that every term that is left over should have an h in it, which means we can factor out an h. So you can't actually just cancel out an h beforehand. Like I can't just cancel the h on the 2h and the h in the denominator. I have to be able to factor an h out in order to cancel. Now I can cancel. So I have the limit as h approaches 0 of 2 plus h. And now I can evaluate at 0 and I get 2. Now I don't know about you, but that seemed like a lot more work than what we did in example number 2. And so I wouldn't necessarily use this method if it didn't tell me to. But the reason why we do is that it starts to get at the idea of the derivative function. So instead of just having the slope at a certain value, so like in number 3, the slope at 1, I can start thinking about a derivative function that would give me the slope at any value. And so essentially what we have is just the same formula, but I've replaced the c with an x. So it's a variable x. So I could find the slope at any point x. So what's going to happen here is I'm not necessarily going to get a numeric answer. I will get an answer that has variables in it. So then I could plug in at the variable and actually figure out what the slope is at a certain x value. Sometimes you will see this with delta x's instead. Delta x is change in x, which is really just h here. So don't get confused if you see the delta x. So just a little vocab, the word derivative is a noun. And so if I want you to find the derivative, I will not tell you to derive. That is not the term. It's called differentiate. So differentiate is the verb that means to find the derivative. So in example number 4, it says to differentiate f of x, which is negative x squared minus 4x plus 1. So notice it's not telling me to find the derivative at a certain value. That means I need to use my formula. Let's scroll back up. This formula right here. Okay, so f prime of x. So I'm going to go ahead and write it out. F prime of x is equal to the limit as h approaches 0 of f of x plus h. So when you write that out, I encourage you to write just wherever there's an x, replace it with parentheses right now. Negative of x squared minus 4x plus 1. Since this is f of x plus h, then I'm just going to put x plus h in the parentheses. So notice wherever there was an x, I'm replacing it with an x plus h, and I'm subtracting f of x. And so I can just rewrite what my function was. All over h. Now we get to do some algebra. So again, remember when you're expanding these, negative of x plus h squared, I have to FOIL the x plus h times x plus h. So I have, and then don't forget to distribute your negative as well. Negative x squared minus 2xh minus h squared minus 4x minus 4h plus 1. And then distribute the negative on your f of x as well. Plus x squared plus 4x minus 1 all over h. Now comes the fun part. Let's try to see how many things cancel out. So the negative x squared and the x squared cancel out. I don't see another 2xh. I don't see another h squared. The minus 4x and the plus 4x cancel out. And the plus 1 and the minus 1 cancel out. So if you look at the terms we have left, you'll notice they each have an h in them. I'm still going to go ahead and rewrite it just so I can see that more clearly. Negative 2xh minus h squared minus 4h all over h. And since each of the terms has an h in it, I can factor out an h. And once I've factored, I can cancel. And then I'm evaluating the limit as h approaches 0 of negative 2x minus h minus 4. So what you want to pay attention here is that I'm only plugging in 0 for the h. And so then my answer is negative 2x minus 4. So this gives me the derivative function. And so instead of just telling me the slope at a certain value, it would tell me the slope at any x value that I want to plug in. So let's actually use that for part B. So since I know that f prime is negative 2x minus 4, then I can find the slopes at different x values. So for example, I can find the slope at negative 4 just by evaluating my derivative at negative 4. So I'd have positive 8 minus 4, which is 4. I can do the same thing at negative 2. Negative 2 times negative 2 minus 4. I will get 0. And if I evaluate at negative 1, I will get negative 2. So this method is more convenient when I have multiple values to find the derivative of, so that way I didn't have to do an equation every time I wanted to find a different x values, or the slope at a different x value. Now let's actually think about what that looks like for the graph. So here's the graph of our function f of x. And let's actually sketch in the tangent lines. So at negative 4, I'm going to go up to the graph. It's at the y value 1. I'm going to try to draw my tangent line here. It's not going to be perfect. Not perfect at all. That's an estimate. It's hard to draw on here. At negative 2, this one should be a little bit easier. And at negative 1. And so if you take a look at those lines that we drew, for this first one at negative 4, it does look like it has a slope of 4. So I can see it's not perfect, but I could go like up 4 over 1. That's a slope of 4. At negative 2, I can see that I have a horizontal tangent line. That's a slope of 0. And at x equals negative 1, I can see that my slope is negative 2. I can go down 2 over 1. And so that is where these values are coming from. Now the next thing that we're going to do, just add on a little bit more complexity, is find the equations of those tangent lines. And so in order to do that, we're going to use the point slope formula. So remember from algebra 1, algebra 2, etc., the point slope formula is y minus y1 equals m times x minus x1. The only thing we're going to make different here is that m is the slope of the tangent line. So that means it's our derivative. So if we know that the slope of our tangent line exists, then the equation of the tangent line is y minus f of c, which is equal to f prime of c times x minus c. So we're just using f prime of c there for our m, our slope of our tangent line. So you need two things. You need a point, so you need your f of c, and you need your slope, f prime of c. If you have both of those things, you can write your tangent line equation. Okay, so let's actually find the equations of those tangent lines. So the first thing you need is a point. So I need f of negative 4. Now I can look at the graph and I see that that's 1. I could have also plugged it into my function, but because I have the graph, it's easier to see. So that's negative 4, 1. My slope is f prime of negative 4, which I found in the table above was positive 4. So then my equation is y minus my y1, which is 1, equals my slope, 4, times x minus my x value, negative 4. Now, leaving it right here is what you would want to do on the AP test. You would not have to actually simplify that. But since we're working it out together, let's go ahead and simplify it. It will also help us match up with the graph a little bit better. So I have y minus 1 equals 4x plus 16, and I can add 1 to the other side. So I have y equals 4x plus 17. And if you look at the graph above where we sketched our tangent line, that seems to make sense. Can't see that y-intercept, but 17 seems like a reasonable answer. All right, let's look at the equation of the tangent line at negative 2. My point, so I'd find f of negative 2. When I look at my graph, I see that that's 5. So I have the point negative 2, 5. My slope is f prime of negative 2, which we found was 0. So my equation is going to be y minus my y value, 5, equals my slope, 0, times x minus my x value, negative 2. So the right side cancels out completely to be 0, and so then I can just add 5 to the other side, and I get y equals 5. That makes sense. When I have horizontal lines there, the equation is just y equals something, and I can see that my graph, or my tangent line up above, is crossing at y equals 5. Last one, equation of the tangent line at x equals negative 1. So my point, f of negative 1, I could see that that was 4. So my point is negative 1, 4. My slope is f prime of negative 1, which we found to be negative 2. And then I can plug that into my equation. Y minus my y value, 4, equals my slope, negative 2, times x minus my x value. Let's go ahead and simplify. Negative 2x minus 2, and add 4 to both sides. I have y minus 4 equals negative, sorry, not y minus 4, just y, equals negative 2x plus 2. And I could see on my graph up above, it seemed like my tangent line would cross the y-axis at 2.